Right. So we have been looking at representation learning, various aspects of it, and specifically, we spent some time on transfer learning techniques, and then we finally moved to domain adaptation, which we had seen one method. I mean, we had seen a supervised domain adaptation method, and the general idea was that what you call as domain adaptation is that you have a task on which you have trained a model, but suddenly the location where you were to deploy your model, that location has maybe some data for the same task, but it's this data is not exactly the same or the same type of distribution as your data that you trained on. Say, for example, I think we had given an example in the last class before that we had, which is that you learned a system or learned a model for basically classifying comments as positive, negative, or others for, say, movies, and now suddenly I give you shopping product reviews, and then I ask you to use the same model for that. So even though you're still maybe required to provide annotations like, say, positive comment, negative comment, and so on, the task is still the same, but the underlying type of reviews that you generally get for, say, movies will be significantly different as compared to the type of reviews that you get for some products on some shopping websites. Okay. So we had seen that, we had looked at the supervised domain adaptation technique where you had some training data available for your target domain as well. I mean, you anyways had enough data available for your source domain, labeled data available for your source domain, but you had a comparatively less amount of target domain data available. Okay. So we had seen one technique how to deal with such a situation. That was the case of a supervised domain adaptation. Now, we move to another scenario for domain adaptation, which is the unsupervised domain adaptation, where in your source domain, you might still have a good amount of data that is also labeled. However, in a target domain, okay, even though the task is still the same, you have labeled data, but you don't have labeled data, you only have unlabeled data. As a result, the supervised learning techniques that you would have used will no longer function in this. I mean, not no longer directly function in this particular setup, because your unsupervised samples will not have any labels. So if you are looking for any, I mean, the previous method that we looked at was actually trying to reduce the distance between, elements from the source and target domain that belong to the same class. That is something you can no longer do because you don't have any concept of class, at least at this end. You don't have labeled examples at the target. So that's where your unsupervised domain adaptation comes into play. And this is a very famous paper that we'll discuss briefly. And it laid a foundation for a lot of other domains as well, with specific technology or specific, say, method is known as a gradient reversal. I will look into that, exactly what that is. Okay. So we'll describe the setting again. When the target domain does not contain any labeled examples, a supervised domain adaptation will generally not perform well, because in supervised domain adaptation, you tend to use that information about this in labels that are available for your target domain, as well as because these labels are common for both your target and your source domain. So you generally tend to use that information in your supervised domain adaptation setup, which is no longer possible in your unsupervised domain adaptation. So we'll have to deal with this some other way. So this particular paper, which is unsupervised domain adaptation by backpropagation, um, in this particular setting, you will have, as mentioned earlier, you'll have sufficient label data in your source domain, but you'll only have unlabeled samples in your target domain. And generally, I mean, even in any sort of payload applications, if you're asked to collect data, it's easier to collect unlabeled data compared to, say, maybe labeled data, because for obtaining label data, that has to be annotated by some person, and depending on the scenario or setting, the annotator also has to be an expert, maybe, or at least knowledgeable about that particular domain. Otherwise, that person will not be able to correctly label these samples. Okay. Right. So there is a domain shift involved, and as usual for domain adaptation, your model has to be updated to perform well on the same task. But even after this domain shift, it should still be able to predict or make some predictions that are good for even this particular domain, even though the labels are same, but your data distribution has changed. Okay, so in terms of architecture, it's a pretty straightforward architecture, and in the diagram you can see actually the three colors representing the three components that the architecture has. So you have your feature extractor, okay, which basically is the initial portion of any deep learning network, is generally known as a feature extractor because it's supposed to provide good features which can then be used for subsequent tasks or say downstream tasks given any input image. So you have a deep feed forward feature extractor. You have a label predictor which predicts the class labels and which is finally objective also. You need to, this is the, you need to finally when you deploy your model, you require this portion only. You have your feature extractor and your class label predictor. Okay. So this will predict class labels and it will be used both during training and test time. And finally, you have the domain classifier. Okay, it's a parallel network that takes input from the feature extractor. So after the feature extractor, the network actually bifurcates into two halves. One is for the label class label prediction, and other is for the domain prediction. Okay, which the task is basically to say of this domain classifier whether this particular sample belongs to the source domain or the target domain. Okay, so the objective of unsupervised domain adaptation through this particular method is that you should be able to perform this classification well, irrespective of whether the sample belongs to the source or the target domain. Okay, but since the source and target domain data are actually, there's some difference between them, we'll try to make these features, the features extracted by the feature extractor, invariant to the domain. So that's the important term that we'll be looking at in the future slides. We want to make these features domain invariant. And a very simple way of performing domain invariance is that if I have a domain classifier and your whatever image I give to you, I can predict the correct domain for that, whether it belongs to source and target domain. What I'll try to do is that I'll try to update this feature extractor in such a way that your domain classifier is no longer able to differentiate between the source and the target domain. If I can do that, that means I have sufficiently modified my feature extractor such that whether I give it a source image or a target image, the feature extracted by it will be similar. If they are from the same class, they will be similar. They'll be close to each other in the feature space. If they are from different classes, they'll be different from each other in the feature space. But even though they may belong to different domains. And if that can be achieved, your classifier automatically will perform well even in your target domain as well. So that's the core idea behind your this particular method of unsupervised domain adaptation by backpropagation. So we'll look at this particular method step by step. So these are the individual classifiers that we have. We have your class label predictor or classifier, and you have the domain classifier. So these individual classifiers are trained to minimize their training error. Okay, their error on the training set. So obviously your domain classifier will be trained to perform well for domain prediction with the source of target, and label classifier will be used to basically perform well on label prediction. So which belongs to, say, if you have 10 classes, so which class this particular image belongs to. Okay. But the point is, if your domain classifier works well, then that means the feature extractor is not removing the domain information from the features. There is some information available. So even though the domain classifier will be trained to perform well on this domain classification task, we will train the feature extractor to perform well only for the prediction label prediction class, but not on the domain classification class. Okay. So we'll see how to do that basically. It's actually a very neat idea. So the parameters of the classifiers are optimized in order to minimize their error on the training set. The parameters of the underlying deep feature mapping or the feature extractor are optimized in order to minimize the loss of the label classifier, but maximize the loss of the domain classifier. Okay. So you will update this feature extractor in such a way that your label predictor works well, but your domain classifier is not able to differentiate between the source and target domain images. So we'll see how to do that. It's a simple trick will basically achieve this thing. So we'll see how to do that. Okay, and if you can do that, you will be able to achieve some domain invariant features. And once your features become domain invariant, your model that was working for your source domain will also work for your target domain with some good enough performance. I'm just checking if I'm audible or not. Yeah. Okay. Okay. Right. So our training step will involve a set of steps. So first of all, given an image from the source domain, the feature extractor will obviously extract some features from it, and it will pass it on to your label predictor as well as your domain classifier. Okay. The label predictor will predict the class label, and the domain classifier will predict whether it belongs to the source and the target domain. So initially the model is untrained. So maybe both the label predictor as well as the domain classifier will make mistakes in these predictions. And that is where your training comes into play. And given, say, an unlabeled input image from your target domain, we will only check whether the once the feature extractor extracts these features, we will only check whether the domain classifier is predicting the correct domain or not. Why we cannot use the features from the unlabeled image for the label classifier? Because we don't have any corresponding ground truth label for our target domain images. Okay. So your source domain images gets to manipulate both the label predictor as well as domain classifier, but the unlabeled input image can only work on the domain classifier. But obviously the feature extractor still remains common for both of them. Okay. Obviously we have not gone to the training portion of it, but the training portion will be slightly different for your label and domain predictor, and a combination of the two things will be happening at your feature extractor. Okay. So the overall method will reduce the label prediction loss using the source domain images, because only the source domain images get to access these particular section of your network. Okay. And somehow we have to achieve domain invariance, at least in the features that your feature extractors are producing. Okay, we'll see how to achieve that. Okay, right. So in order to make the features domain invariant, we are going to do a few things. So at the training time, we will maximize the loss of the domain classifier while you're optimizing, say, your feature extractor. That is this thing. While simultaneously minimizing the loss of the domain classifier when you're optimizing this particular section of your model. So within the same model, you have two sections that are behaving differently for the same loss. The loss is the domain loss classifier loss, but on that same loss, this particular section will be optimized to reduce the loss, whereas this particular section will be optimized to increase the domain classification loss. And the whole point being that I want to optimize a feature in such a way that your domain classifier can no longer recognize which domain a particular image belongs to. Whereas we'll also have to train the classification part, label classification part. So even if these features do not provide any domain information and become domain invariant, they should still contain information about the class labels at least. Okay, so that's the idea. Yeah, so that's what I said. We'll minimize the label prediction loss. That is something we'll not do. Yes, Prabha is asking some question.
It's a good question. So we already in the first iteration we tend to
Can you
increase the
be
loss.
a bit louder? I cannot hear you.
It's raining heavily. Okay, let me know if you can hear. So in the first section, we tend to increase or to increase the loss, right? And that makes the domain already domain classifier as the lowest of the level. Why we need to again set the domain classifier for the other iteration for higher loss, sorry, lower loss value?
See, what will happen is that if I don't try to reduce the domain classification loss, okay, this particular domain classifier will be a very poor classifier. Okay, and if it's a poor classifier, it will be very easy to fool the domain classifier. So it's just like saying that suppose if the feature still contains domain information, but my classifier is so bad that it cannot even read that domain information. Okay, so then even if this particular classifier is performing poorly, there's no guarantee that the domain information does not exist in the features. So we want to make this domain classifier as good as possible, and also update the feature extractor to fool a strong domain classifier, which means if there is any bit of domain information available in these features, this domain classifier will able to catch on to that and make the predictions. So that will ensure that as much as possible, we are removing all domain information from your features. Okay.
Got it. Thank you.
Okay. Right. Yeah. Shubhadeep.
Sir, is there any way you can explain it by an example? Let's say we have an unseen data of, let's say, dogs and cats, and from here in this aspect, how does this overall pipeline kind of extract the features and then the domain
Okay.
classification, how it does?
Okay.
Yes.
So suppose your task was initially, as you said, to identify between dogs and cats, but your domain was maybe Indian dogs and cats. Okay, your source domain, and your target domain is now that you're looking at Egyptian dogs and cats. Okay, so it's still dogs and cats, but maybe the data or images that you get or the type of breeds that you get for these dogs and cats might be slightly different. Okay, so you have enough data for your Indian dogs and cats, labeled data, so you know which one is a dog, which one is a cat. But for Egyptian set, suppose I've only given you images and I have not given you the labels. So you have a lot of images of cats and dogs. As a human being, I know which is a cat, which is a dog, but I do not have any associated labels. Okay, so this is unlabeled data and this is a labeled data. Now in this particular setup, what we do is that we pick labeled examples of, say, cats and dogs from the source domain and pass it on to this feature extractor. Now what happens? You extract, the feature extractor produces some features from this image and passes it on to the class label predictor as well as to the domain predictor. Now the class label predictor, if it is a dog image, will try to predict dog, and the domain predictor will try to predict that it belongs to the source domain. Okay, this is the prediction, and now based on this, I mean, this is the ground truth. So you have your dog class and your source domain for both the predictor. And now based
Source
on this,
is Indian.
source is India. Source is India.
Okay, understood.
Huh. So now what you do is that you train your model in such a way that you try to reduce this loss while optimizing this section. You try to reduce the domain loss while optimizing this section. But while optimizing the feature extractor, that basically, because once you do backprop, at the end, both these losses will also affect your feature extractor as well. So over here, what you do is that you will try to decrease the label loss, but you will try to maximize the domain loss. So over time, and obviously you also have your target image. So when you give your target image, you extract features and only pass it on to the domain classifier. You don't have labels, so you cannot do this particular training for the class level predictor. So over time, what will happen is that this particular feature extractor will start removing as much of possible of traces of domain information from the features, so that your domain classifier does not work, whereas it will retain information that are important for class level prediction. Okay, so at the end of the day, when you are able to do this properly, your predictor, class level predictor, which was, remember, this section was only trained on Indian cats and dogs, will also start working for your Egyptian cats and dogs, because the features that it's using has become invariant to the domain.
So the objective is to remove the bias of that Indian thing.
Yes.
Okay, yes. Okay, understood.
Right. Now this thing, yeah. Yes.
Sorry, sir. The first bullet point, I'm not able to still. I know you.
This one?
Yeah. So
Yeah.
it says maximizing the loss of the domain classifier while optimizing the
While
feature
optimizing
extractor.
features.
And then simultaneously minimizes the loss of the domain classifier. So it's the same. It is minimizing as well as maximizing
Yes.
while optimizing
So
the.
just think about this as 3 separate networks. Okay. 3 separate networks and 2 losses, one for class, one for domain. So this, in this particular first bullet point, you're only looking at the domain loss. So the one single image passes through your feature extractor and reaches both the branches as well. So when you're optimizing your feature extractor, in your feature extractor in terms of your, say, domain loss, you will try to maximize this particular loss. And when optimizing
Sir,
your,
logic of maximizing means why we want to maximize it.
see, let me again show this. So suppose you have your feature extractor and your domain classifier. Forget about the label pattern. You have a domain classifier and you have a feature extractor. Now, this takes an input as some image and produces some features. And that features goes into the domain classifier, and that domain is able to say whether it belongs to the source or the target domain. Okay. Now, what I'm trying to do is, I'm trying to delete any information that might be useful for your domain classifier in the features. So if, say, your features contains, suppose it's a feature of, say, 512 size vector, and suppose out of this, the last 10 positions of this vector actually contain your domain information. What I'll try to do is that I'll try to, obviously I don't know where the domain information is stored, but if suppose the last 10 values is corresponding to the domain, I'll try to zero out these domain values for all the images. If I can do that, your domain classifier has no way of knowing which domain this particular input image belongs to. This is just an example. It will not happen that only a few set of values will or a specific position will have your domain information, but just for representation purposes, it will try to remove all possible ways that your domain classifier can identify the domain. If I can do that, what I'm essentially doing is that your domain classifier will no longer be able to extract the domain information from the features. Parallelly, what I have done, I am also training a simple classifier for the labels. And that will ensure that even though I've removed the domain information, I still have class information available that helps me to predict the class.
Oh, okay, got it.
Okay. So I'm still able to,
क्योंकि वहाँ पे डोमेन इंफॉर्मेशन हट गया, लॉस ज्यादा है उसका, तो ज्यादातर चांसेस होगा क्लास इंफॉर्मेशंस प्रॉपर्ली होंगे, तो वो सही से
exactly. हाँ.
Sir, I understood that part, but the alternate between maximizing as well as minimizing,
yes,
that part is something that
that will cover next. So that how to achieve that, we'll see that.
Okay.
Right. So in order to achieve this thing, because you have the same loss and you're basically doing two types of optimization based on the same loss, we use something known as a gradient reversal layer. And as the name suggests, so whenever you do backprop, you basically are sending back your gradients that you're calculating, right? So, I mean, you must have looked at the backprop, you've covered it during the first fractal. So you're passing back chain rule, you're passing back basically the gradients that you calculate to all the layers. So starting from the last layer to the first layer. So gradient reversal layer, what it does is that it simply multiplies the gradient that you're passing back from the first layer of your domain classifier to the last layer of your feature extractor. It multiplies that gradient with a negative value, maybe a negative lambda. And effectively what it does is, remember that whenever you're doing your backprop and you're trying to update it using, say, gradient descent, you do something like this. You have your old weight and you subtract some, based on the loss that you have gotten, you subtract this particular gradient information from your original weight value, and that helps you to basically optimize your model. If I change the symbol over here, because why do we generally say this minus? Because suppose if you have a loss function that looks like this, and suppose here you have the minimum loss, and suppose currently whatever weight value you have, you're getting a loss somewhere over here. So what you'll try to do is that you'll try to reduce the value of x, or basically not x, this is the weight actually. You'll try to reduce the value of x so that you come closer to a situation where you have zero loss or maybe a very low loss. Okay. So now if I suddenly change the symbol, suppose I was supposed to go in this direction. If I change the symbol, I'll start moving in the opposite direction where your loss will actually increase. Okay, that is exactly what you're trying to achieve over here. So up to this point, you're using the usual gradients. So these weights are getting updated in the standard manner where you're subtracting the gradient. But once you go through this layer and you move into the feature extractor, you start adding it instead of subtracting this thing. Okay. So as a result, if the loss would have been reduced by moving in this direction, now since you're changing the direction, your loss will not decrease, it will start increasing. Okay. But which loss are we considering? We're considering the domain loss. Okay. Will not do the same thing. This gradient reversal layer will not be applied to your label prediction. So even though you're making incorrect movements with respect to your domain label, but with respect to your class level, you'll be doing the usual gradient only. So there'll be no change at least in terms of that. Okay, and that's the objective of your gradient reversal layer. It does not have any trainable parameters because, as you can see, it's just a say a negative constant value that you're multiplying. Maybe you can do some validation to come up with a hyperparameter value for lambda, or maybe you can use -1 directly. That's also fine. Yeah. Okay. Right. So during the forward propagation, this particular layer will not behave anything not suspiciously. It will simply pass on whatever values that are passing through it. So it will act as a layer which has no specific learnable parameters. But during backward propagation, it will take the gradient from this particular level and it will multiply by this minus constant, and then it will pass it on to the preceding layer, which is the feature extractors layer. Okay. And that's how you basically achieve this particular sort of gradient reversal. And obviously during testing, you will not have the gradient reversal layer. You will discard the gradient reversal layer, you discard the domain classifier, and you'll only use the feature extractor and the your label predictor. Okay. Right. So that's the idea. So any doubts up to this point?
So for the domain classifier, you're not doing any kind of learning, right? You're just taking the gradient and then passing it on to the first layer.
No. We are doing training. So the thing is that, as I said earlier, consider these three as separate subnetworks. So for your domain classifier, you will be, while optimizing the domain classifier, you will be using these gradients only to reduce this loss. So basically, if your loss gets reduced in a particular direction, so you will try to move in that direction for at least this portion. But once you move over here, you have inverted the gradient value. So even though the feature extractor does not know that you have inverted the gradient value, so in its internally, it's thinking that I'm still updating my weights in order to reduce the domain classifier loss. But since we have inverted the gradients, what will happen is that these set of parameters will get optimized in order to increase the loss that you're getting for your domain classifier. So you are training both the domain classifier as well as the class simple label predictor and the feature extractor, but the loss that you're optimizing and how you're optimizing, that is different for the three subnetworks. Okay. Okay. Right. Any other questions?
Sir, why is it, I mean, in the third point you mentioned that GRL acts as an identity transform? Why
so when you're doing forward propagation, it has no business over there. So it does not have to do any work over there. So it's simply whatever value you give in the input of this gradient reversal layer will also be the output. That's why it's known as identity transform. So it's at the end of the day, it's an official layer, right, through which your intermediate inputs has to pass through. So while forward propagation, it will not make any modification to the intermediate data that you're passing through. It will pass it on as it is. So that's why it's known as identity transform.
So what is intention to multiply with minus lambda in the gradient?
So
to reduce the slope, what?
No, see, if you remember the backprop thing or gradient descent thing, remember that suppose this is the, you pick any specific weight value. Say you have a weight over here that is W1 and you have a weight over here that is W2. Now you have some corresponding domain loss associated with it. Okay. So when you get a domain loss for a so currently say maybe the value of W1 is somewhere over here. Okay. And the corresponding loss that you get is here, somewhere over. It's a high loss. It's not a low loss. So you're trying to reduce the loss as much as possible. Now, when you do your gradient descent, you'll get that the direction of the gradient is this one. You'll try to move in the opposite direction of the gradient. So you'll get that you should move in this particular direction, so that your W1.
Like normally, what we know, like where gradient in 0 means that is a kind of either a minima or maxima.
Yeah. So remember that in your say gradient descent, you try to move in the opposite direction of your gradient. So gradient direction will actually move you, so in this particular case, to a maxima, but you're trying to reduce the gradient value, the loss value. So we'll try to move in the opposite direction of your gradient. Okay. Only consider this particular portion for now.
Okay.
So now what will happen is that you will shift your W so that your W comes somewhere over here, and where you have a very low loss. I think this particular thing would be 0, but anyways, so you get a 0 loss. Now, so if you continue to do that, your domain classifier gets to train very well, and it has a loss of 0. That means it is working very fine. Okay. Now consider the same loss, but for W2, a weight that is over here. Okay. So for the same loss, say for W2, you are currently over here somewhere. Okay. So because when you do backprop, this gradients from here also will reach here. Now for W2, I want to optimize W2 in a way so that the loss domain actually increases, not decrease, but increase. So if I want to increase this loss, I have to move in this direction, which was opposite to the direction in which I was moving over here. Okay. So what do? I basically I multiply the this domain, this gradient that I have with a negative constant. If I do that, while I was supposed to do a movement in this direction, I'll start moving in the opposite direction, where the loss will actually increase.
So one general question, sir, why we want to increase loss in the feature extraction
yes
layer?
Not both the losses. We want to increase only the domain loss, while we're trying to reduce the loss for your class predictor, because we want this particular feature extractor to give me good information so that I can extract whether it's a cat or a dog. Okay, that I want to do, but I don't want it to contain any information about which domain this cat and dog belong to. Maybe if it's an Indian cat and dog, or it's an Egyptian cats and dog, I don't care. So I'll try to reduce as much of information as possible, such that your domain classifier is not able to identify the domain from these features. If I can do that, what you have effectively done is that you can use the same classifier for your target domain for which you have no label data, which is your Egyptian cats and dogs.
इसका मतलब है सर, जो W1 से फीडबैक आया था, उसको वो लॉस हम इंक्रीज करना चाह रहे हैं, क्योंकि हम W1 वाले सेक्शन में मैक्सिमम लॉस रख रहे हैं, ताकि हमारा ये जो क्लास लेबल है, ये करेक्ट इंफॉर्मेशन हमें दे, क्योंकि W1 पूरे सब्सट्रैक्ट हो जाएंगे, तो उसमें केवल क्लास की ही इंफॉर्मेशन रह जाएगी, सो वो इजीली समझ पाएगा कि किस क्लास से बिलोंग कर रहे हैं.
हाँ, बस सब्ट्रैक्ट मतलब वो ऐसे नहीं है, पर ठीक है, आइडिया वही है. बेसिकली यू वांट टू रिमूव एज मच एज पॉसिबल कि डोमेन का इंफॉर्मेशन ना रहे, बस क्लास का इंफॉर्मेशन रहे इसमें. ठीक है.
That's why we increase loss in this W2 section.
हाँ, W2 section में we try to use the negated gradients of that is following from this particular path. तो उसका नेगेटिव ग्रेडियंट हम यूज कर लेते हैं rather than the usual gradient जो भी हमें मिल रहा है.
तो सर, जो इससे फीड फॉरवर्ड जो आया है क्लास लेवल से, उसमें पॉजिटिव ग्रेडियंट रखेंगे फिर, ताकि वो प्रॉपर.
हाँ, इसमें तो पॉजिटिव ग्रेडियंट ही रहेगा. जो ग्रेडियंट है वही फ्लो हो जा रहा है.
हाँ, ताकि
कोई रिवर्सल नहीं है,
मिनिमम करता चला जाए और इधर से मैक्सिमम करता चला.
Exactly. Yes, I think someone is asking a question.
So sir, in case of W1, so instead of taking any region, we have taken the W1 in the left hand side of the slope. Maybe we may take it in the right hand side of the slope. So that
No,
we
no, no.
can
I'm saying I'm giving you a situation. मैं एक situation बता रहा हूँ जहाँ पे where you have the W1 at a situation where your loss
So basically
currently
it's
loss is
situation
question
based.
पे.
So that is
Situation based.
situation.
यहाँ पे
Okay.
भी हो सकता है
That
ना.
that may be negative and that can be positive, right?
हाँ हाँ हाँ. जैसे suppose अगर इधर होता, ठीक है, W1 का अगर इधर होता, then in this case in domain classifier will try to move W1 in this direction ताकि loss zero हो जाए.
Mm-hmm.
ठीक है. But W2 will try to move this in the opposite direction ताकि loss maximum हो जाए.
That
ठीक है.
case,
No matter which
minus
slope you are
lambda.
there.
Okay, so in that case, we would have the lambda and gradient the positive one, right, instead of negative, right?
नहीं, we will always do minus over here. पर क्या होगा कि depending on where you are landing, gradient ही उसका
Actually, we are
negative हो जाएगा तुम्हारा.
okay. Actually, we
है
are moving towards the
हाँ.
the lower side.
जैसे
That's the reason.
हाँ exactly. तो इधर में तो ऐसे भी gradient negative ही है और इधर positive है. So whatever is the direction, we add a we multiply with minus. So वो direction जो भी है वो reverse हो जाएगा.
So the loss
Can we ask one question?
Yes.
Go ahead.
Yes. So, sir, can we do this for text classification? Suppose if there is a text comprising of English as well as German language, like good morning, Pratik, and good morning. So, can we get the distinction that good morning is English and in domain classifier, good morning, Pratik is German?
नहीं. So what you are saying is two languages. तो वो तो simple classification ही हो गया.
Okay.
You don't require domain in that case, na. So you have one text in German, one text in English.
Yes.
So it's a simple classification whether it's German or English. तो उसमें domain as such आएगा नहीं unless until you want to do say you're trying to predict whether the comment is positive or negative. कुछ sentiment classification you're doing. Then you can say that task मेरा sentiment classification ही है, पर initially मेरे source domain में सारे text English में था और target domain में सारे text जो है वो German में है. So I think that situation will fit this better.
But this network we can also use for text classification.
Not this specific network. ये तो image के लिए है, तो you have convolution layers and all. You will require FC layers or whatever other network that you're using for text classification. कर सकते हो. अब structure यही रहेगा, पर your components हो सकते हैं अलग.
Okay, thank you.
But sir, the situation that you gave, like the text is in German and English, so first we have to train it to understand German and English, right? Then only.
So yeah, for text, usually what you do for text is that you use some standard word embeddings. जैसे suppose you're using say word to vec या कुछ और जो available word embeddings है. तो वो जो training portion है that gets taken care of for text.
Okay.
So at least it knows how to extract features from that.
And so the effect of this training, say we have the first iteration. So in W1 is getting decreased, we reduce that. For W2 we are trying to increase, right?
Yes.
And the second iteration, the W1 will be landing higher than the previous one, right? I mean, we will be still effectively moving. The loss will be increasing while we will continue to pull it down. But eventually, all the iterations are going to slowly pull it upwards only, right? Because of the
Yes, and no. So what will happen is that over time, if you don't have any domain information left in your features, this will not function well. Your W1 will not function well no matter how much you optimize it. So you're correct in saying that over time what will happen is that your LD loss will keep on increasing only. And at one point it will, what happens generally is that at one point of time your other classifier will work fine, but your domain classifier will have high loss, will not be able to extract any information, will not be able to optimize it further.
Right. So effectively, even though we are programming it to reduce, but the effective combination is making it increase over.
Yes. But because we are programming it to improve, that will ensure that all possible information that could have been used for domain classification will get eliminated first before this this part becomes totally hopeless. Before that, at least कुछ भी अगर information बच गया है, it will try to still be able to predict your domain. But after a point, when most of the information is gone about the domain, this loss will, there's no way of recovering this loss.
Okay, and the loss function of the domain classifier and the extractor, these are actually different loss functions, right? Or they are one loss.
It's still cross entropy loss only. It's simple classification loss. So both of them are classifiers only, right? So here you have labels, here you have two domains. So you have 0, 1 prediction over here, and suppose you have 10 classes, you have 0 to 9 outputs. So you'll still be doing cross entropy loss only, simple classification prediction loss. But how you're utilizing the gradient, that differs when you're doing backward.
And whenever we are training the domain, we keep the class label constant, and whenever we are doing class label, we keep
No.
You cannot change both
That
of
is-
them at the same time.
No, actually, this, so what, see, for your simple images, I mean, for your source images, anyways, you will be passing these features to both your class predictor as well as your domain predictor. So you're parallelly training them.
Thanks.
So one general question, like in this theory हमने डोमेन एडॉप्शन किया है, डोमेन को इंट्रोड्यूस करा है, तो इससे एक्चुअली लर्निंग में स्मार्टनेस कहाँ से इंप्रूव हो रही है? मतलब केवल ये तो देखने में ऐसा लग रहा है कि ये डोमेन रिलेटेड इंफॉर्मेशन इमेज से रिड्यूस कर दे रहा है, तो क्लास के पास केवल डोमेन नहीं है, मतलब नॉर्मल डेटा बच रहा है, इसके अलावा ये कोई और इम्पैक्ट होता है क्या?
नहीं, the point is that हमें इसका जरूरत क्यों पड़ा? हमें जरूरत इसलिए पड़ा क्योंकि we had a target domain जहाँ पे लेबल डेटा था ही नहीं, ठीक है? हमारे पास सिर्फ सोर्स डोमेन था जिसमें एनफ डेटा, लेबल डेटा था, तो हमने एक मॉडल तो बना लिया सोर्स डोमेन का, बना सकते हैं हम सोर्स डोमेन का, पर टारगेट का नहीं बना सकते. तो टारगेट का बनाने के लिए वी कम अप विद दिस एलैबोरेट सेटअप, ताकि योर क्लासिफायर स्टिल, जो लेबल प्रेडिक्टर है वो अभी भी सोर्स डोमेन का ही इमेजेस का ले रहा है, whereas your target domain image can only go to your domain predictor. But with this setup, you're also coming up with a classifier that works for both your source domain as well as your target domain. Requirement था, इसलिए हमने किया, नहीं तो अलग से कुछ.
We are removing all the things of domain classifier. We are trying to remove all this.
Yes.
Right?
Yes.
सर यहाँ पे जो डोमेन है और जो हमारे लेबल्स हैं, that has to be in some topology or it can be separate of topology. Like for example, we are talking about dog as a label and a German dog as a domain, right?
Yes.
It has to be some kind of topology. Like let's say for example, if I talk about fashion industry or maybe oncology, so if there is certain kind of topology, then only this works, or it can be independent.
See, it can work in, see, it depends on, in this particular setup, you're looking at some sort of a shift that has happened between your source and target domain.
Mm-hmm.
Suppose if I'm dealing with dogs and I have already incorporated all types of dogs, so I have already have German Shepherd and other things in my source domain itself, then I don't require this setup. The problem comes when, suppose you have trained using, you trained for dog classification using say two breeds of dogs and 2 breeds of cats, and now in your target domain there are further breeds of dogs and cats, but वो labeled नहीं है, and because your model has not seen those breeds of cats and dogs, there's a very high chance कि वो that can make some mistake over there, क्योंकि there has been a domain shift or some sort of shift in the general जो images, how they look, how they appear. There's this general shift in that idea or in that distribution. So your model will not perform necessarily well on your target data again. So that's why we require this particular setup.
Yeah,
Topology in the sense, if you're saying that you have German dog, so German will be a domain and dog will be your class. Would depend करेगा if you have your domain shift is only based on that. Say suppose your domain shift is you had your some Pomeranian or some other Alaskan Husky in your source domain, and your target domain has a German Shepherd dog. So in that particular specific case, हो सकता है you can consider your German to be your domain, but it's not necessary that वो हमेशा वो कोई टोपोलॉजी रहेगा उसके बेसिस पे होगा. कोई भी डिफरेंस अगर आता है डेटा में, किसी भी टाइप का डिफरेंस हो सकता है. A very good example is that you are building a classifier जिसने सिर्फ डेलाइट इमेजेस से देखे हैं, सुबह के टाइम के जो इमेजेस है वही देखा है, और अब जब टेस्टिंग के टाइम आई एम गिविंग यू नाइट इमेजेस, आइडेंटिफाई मुझे अभी कार को ही करना है और मेरा इमेजेस ही चेंज हो गए, सारे नाइट टाइम इमेजेस, तो वो काम नहीं करेगा. So how do you ensure? So वो एक domain shift आ गया data. So this is for that kind of problems.
Okay, I think this example made me more clear that it can be anywhere where my class level is still there, but there is a shift between the environment or between the other parameters which might bring that kind of change. For example, in the night images, the scenario almost changes, right?
Yes.
So the object or the label is there, but the surrounding environment is changed, so that's why there's a shift which is happening. We are also saying that the night images was not at all was there in the source image.
Source domain, yeah.
Okay. Can it be used for also different kind of languages? For example, when we talk about Indian languages, in those contexts also it can be used. I train on maybe Hindi something, and then I want to shift it to and see how it works for something like Marathi.
Yes, so you can do that as well, but for that so as I mentioned, you require some sort of a encoder that knows how to recognize these languages. So some sort of a word2vec or some other language embedding models. So if that is available, and then you on top of that you learn these few specific features that is domain invariant, you can do that as well. That is fine. But the objective will not be translation. Objective will not be translation, or object will not be say identify whether this is Marathi or Hindi. But the objective can be that I want to find out the sentiment, whether it's a positive comment or a negative comment, but my language has changed between these two texts. So we can apply something like this.
Something like that.
So डे नाइट के केस में सर ये टारगेट आप क्या होगा इस केस में?
टारगेट तो वो नाइट इमेजेस है. सपोज यू डूइंग कैट्स एंड डॉग क्लासिफिकेशन ओनली, पर सोर्स डोमेन में सिर्फ मॉर्निंग डे लाइट के इमेजेस थे, और टारगेट डोमेन में सिर्फ नाइट के इमेजेस है. ठीक है, तो योर मॉडल हैज बी, इफ यू ओनली ट्रेन योर मॉडल ऑन योर सोर्स डोमेन, टारगेट डोमेन में इट माइट नॉट वर्क दैट वेल, because your environment will be slightly different, or maybe major.
सोर्स डोमेन का मतलब है जो नॉर्मली हमारे पास डेटा जिसमें ये ट्रेंड हो रहा था, और टारगेट डोमेन मतलब इसको जो टास्क दिया एक्चुअल में करने के लिए.
हाँ, exactly. So target domain is the task that you data, the domain of the task that you're trying to solve. Maybe you have enough data for your daylight images, but not enough data for, or maybe in this case you have no data, no labeled data for your nighttime images.
Nice.
Unlabeled data है पर labeled नहीं.
Okay, sir, got it.
Yes, I think someone else was raising it. ठीक है. We'll brief. Yes. So we'll briefly look into semi-supervised learning, and then we'll maybe end for today and continue the rest tomorrow. So, right. So we have already looked at these setups. So you have a supervised learning setup where you have your training data is fully labeled. You have an unsupervised learning setup where your training data is fully unlabeled. And then you have a semi-supervised learning setup where you have both labeled data as well as unlabeled data. Now, ideally, I might take a shortcut and say, okay, I'll not use the unlabeled samples at all. I'll only use the labeled data. Okay, that's always an option. But this will not be possible if the labeled data is not in good enough quantity. You have maybe few labeled data, not sufficient enough, but you have a lot of unlabeled data. So the idea behind semi-supervised learning is to utilize as much of information from the unlabeled samples in order to help training the data or training your model on your labeled samples. Okay, so there will be some problems obviously associated with it, because you're creating a single model that will have to utilize both your labeled as well as your unlabeled samples, whereas you can maybe train your model on, say, your labeled data using some classification laws like, say, cross entropy laws, but you cannot train your unlabeled data using the same laws. Suppose you're considering a simple network which has, say, a feature extractor and then finally a classification layer. Okay. So even though you train this network using your unlabeled data, the labeled data cannot be utilized. Labeled data, you cannot use the unlabeled data over here, because for this particular setup, you don't have any ground truth label, so you'll not be able to optimize this particular network. Okay. So, but then we still want to utilize both these data, so we'll see how to do that. right? And more specifically, when you look at consider the type of task that you can perform on unlabeled data, it's not classification that you can perform. You can maybe perform clustering or some time machine reduction, other things, but not classification. So how do you incorporate them into a common setup and then utilize it to maybe learn a very better supervised model or semi-supervised model? Okay, and that's the problem. And we'll look into some techniques maybe in tomorrow's class to cover this idea better. Right. So I'll not go into the technique because that will take some time. So any doubts in today's class, if anything is left? Otherwise, we can end today's session.
Sir, the questions we can expect from here are like conceptual questions, or will be some use case based questions? Like in
There can be use case based questions where I'll give you a scenario, because see, we are covering a lot of scenarios and how to specific ways of maybe dealing with situations like that. So I'll give you a scenario and ask you maybe to deal with a few set of problems. How will you deal with it? Questions like that. Also, maybe you have these settings like semi-supervised settings, all of these settings. What is the core idea behind these settings? Why do we need a setting like that? Some questions like that you can explain.
Hi, sir.
Yes.
So, with the interest of exam, how many more classes are expected, sir, in order to cover?
Classes, I think, will continue till I think mid-November. I think, according to the calendar. So we'll see. I mean, accordingly, we'll update the topics and all.
Thank you.
Okay, I think we can end today's session.
Thank you, sir. Have a great day.
Yeah.
Thank you, sir.
Thank you, sir. Bye.